You've mentioned a couple of things that I've seen other companies try to automate kind of on the individual level as part of PCB design. So you briefly mentioned design reuse, and then you referred to things like documentation requirements capture. And one thing that I see a lot of is like the chat with your data sheet kind of thing, which I think
Mhm.
is just, one of the cogs in the machine of requirements capture and kind of front end design tasks. And it seems like you're taking a little bit of each of those things and trying to put it into a code-based kind of ecosystem.
Yeah, I would say if you look, back a year or two at software, I think hardware is in a relatively similar spot. It was very much there's just little completions, little like niche places where you would use an agent to achieve some specific task. Where we see it heading, already in software, obviously, and we see that proliferating to hardware as well, is agents will be able to have much larger scope. They'll be useful to you across the design process, not just to look at a data sheet.
Hello, everyone, and welcome to the Altium OnTrack Podcast. I'm your host, Zach Peterson. Today, we're talking with Ioannis Papamanoglou and Narayan Powderly, co-founders of Atopile. They've been out talking with folks about their new code-based AI tool for PCB design, and we've been talking with several companies in this area recently, so I'm very happy to be speaking with them both today. Guys, thank you so much for joining us. Hopefully I didn't destroy your names. I apologize, but thank you very much for being here today.
Yeah, no worries. Great to be on.
Yeah, thanks for inviting us out.
Yeah, absolutely. So you guys are new guests. I've been talking to all the folks who do AI stuff in PCB design because I think we're really starting to kind of turn a corner on this. So I'm really interested to learn about what you guys are doing. But if you could, before we get started, introduce yourselves to the audience and tell us about your background and how you got started in electronics.
Yeah, for sure. So my background, I was an electrical engineer in a previous life. I worked at a couple of companies. Most recently, I was working at Tesla. I worked on the BMS team there as a design engineer. Used Altium in my day-to-day work. And yeah, sort of out of that, I found, looking over at the world of software, hardware has really been left behind with the tools that we get to use in our day-to-day. So Atopile is trying to bring the advances that have happened over in the world of software and bring some of that back to hardware design as well.
Yeah, so I'm Ioannis. I worked in the Netherlands for most of my career before coming over to the US. And I've been working at a lot of like smaller companies till I ended up in some energy company that wanted to become a tech company. And there I was doing, I was leading the engineering department. That's where I noticed that hardware and software just, for some reason, are implemented very differently, even though like at heart, it's both engineering principles are just pretty similar in the way that we're thinking of things from the beginning till the end. And that's kind of what brought me to this problem space of like, can we bring the best of both worlds somehow together?
Yeah, I'm always interested when I talk to folks who, started in pure hardware and then got into software development, including software for hardware designers. So this is always really interesting. And so you guys are building a company called Atopile. If you could, tell us what was your thought process behind building Atopile and your approach to getting AI to perform design tasks.
Yeah, for sure. So I guess what, just winding back a step, we're thinking about this problem well before AI was around. We're thinking of it more from like an automation perspective. How do we bring automation connecting together, across the design process? All of these steps that today in hardware, there's just a person in the middle of them. You think in software, we have CI, we have GitHub, all of these tools to manage complexity of your designs. And we found that really missing in hardware. So our first step was, well, how can we capture all of these things we're trying to do in a way that just immediately fits into this same ecosystem of tools that exists? So naturally, we landed at, well, it needs to be described in language, it needs to be a programming language to leverage all of that power. I think, in hindsight, it just wasn't going to work because it was way too big of a change for people. And our company got very lucky that AI tools became prolific and very powerful when they did. As what we see has really happened here is the barrier to try new things has dropped through the floor. before, where you might not be using, Python for some little automation. You might just use a little napkin math or some calculator online. Now it's really easy to use AI tools to allow you to build something quite complicated that before just wouldn't have been worth the learning overhead. And we see the same thing happening in our tool. So what would have looked very scary 2 years ago, now you can just interact with in natural language in a very intuitive way. I would argue in some ways even more intuitive than the tools that exist today.
Yeah, what brought us originally into this world of trying to capture information in code is that there's just a lot of intent lost in the tools nowadays. There's great tools out there for electronics design, everything from manufacturing to DFM to schematic capture to layout design, but all those tools live in their small little islands and are very good at that specific niche. But at every stage, I have a new engineer or a new process or something which is very lossy to translate in between. From my requirements capture into my schematic capture, there's always a human in between that has to be in the loop, that has to be stuck in meetings, that has to be re-explaining stuff. While in software, a lot of the information and a lot of the design is captured in one single source. That's just the code, and that one you can use across the whole horizontal layer. And this is kind of where we saw like both Narayan in his background at Tesla trying to scale big amount of application boards, but also from my background where we just try to move as fast as possible, where manufacturers were determining our products primarily, and our mode was how fast we can adopt. We saw that we want to reuse a lot of our design, and we want to be able to automate and have like central authority over how things should be built, and rules are in the same domain as the designs themselves. So that's where we were trying to discover what is the best way to describe engineering intent in a way that we can automate it across layers, but also make engineers' lives more less boilerplate heavy and more actually engineering.
Yeah, this is really interesting because you've mentioned a couple of things that I've seen other companies try to automate kind of on the individual level as part of PCB design. So you briefly mentioned design reuse, and then you referred to things like documentation requirements capture. And one thing that I see a lot of is like the chat with your data sheet kind of thing, which I think is just one of the cogs in the machine of requirements capture and kind of front end design tasks. And it seems like you're taking a little bit of each of those things and trying to put it into a code based kind of ecosystem.
Yeah, I would say if you look back a year or two at software, I think hardware is in a relatively similar spot. It was very much, there's just little completions, little like niche places where you would use an agent to achieve some specific task. Where we see it heading, already in software, obviously, and we see that proliferating to hardware as well, is agents will be able to have much larger scope. They'll be useful to you across the design process, not just to look at a data sheet, but you want to look at a data sheet with them. And then later when you're doing a design, you want the agent to know, hey, we looked at this data sheet, we evaluated these things. You don't want to have to go talk to some new tool that has no idea about the context that you were working on this morning. We really see these agents become much more powerful when you can connect all this together in a way where they see the whole thing that you're working on, not just some little small piece of it.
Yeah, you've mentioned a new buzzword, which I guess is our indicator that the AI bubble is back on, which is now agent. You're one of the few companies that has started to talk about this in terms of what we can do with agents and kind of how they can work across domains and work across tools and things like this. So what is your take on the current state of AI in hardware engineering tasks, especially as some guys that are kind of working on the front lines of all of this? And what do you think the future looks like?
So what we see a lot is that there's finally some excitement happening in hardware with AI. So it's really good to see that people are trying to use it in a way that amplifies their workflows, because a lot of hardware processes are pretty old. So trying to change anything about them is pretty painful. But what we see especially is that most approaches right now are just really scratching the surface. It's just like take a schematic, just run it through an image analyzing LLM to do some image understanding, or here's a netlist, or look at the PCB. Like the AIs are pretty smart. Like, we think that the intelligence is already 100% there for what you would ever want to do for the foreseeable future with LLMs. It's really just the orchestration and instrumentation layer that currently is not there. So we think that agents need to have better tools and better understanding of what you're trying to do and understand what you did, and also what itself is trying to do and what it actually has built. Because drawing some lines on a schematic, the LLMs are getting pretty good, the visual models, but it's still a very high abstraction needed before they understand that a line means a connection. Like, a lot of neural activation has to happen before we have come all the way to the point of those two things are connected. While with what we are trying to do is that the agent has like a representation internally that just is very light to understand. Like, if you just have a one single line of code that just says this is connected to this, and with this way and with those parameters, there's not a lot of thinking required, not a lot of cognitive load, if you would like to think of it, for the intelligence to understand what's going on, and thus it can really leverage its deeper thinking way better to actually do complex engineering.
So yeah, this is interesting because yeah, I would agree that the models are pretty good. It's everything that you do around the models that actually makes any of this really effective. And there seems to be this disconnect between what the AI model, companies actually do and what we need to do, because everyone talks about this in terms of, oh, well, when we have a better model, you can do X, right? Especially the AI companies. And I think that's what they use to justify getting more investment and spending on CapEx and that kind of stuff. But I agree with you guys. I think the model capability is already there. It's just everything around it and how you interface with the model is really what needs to change in order for us to do anything meaningful.
Yeah, I think something we've seen as well is it's definitely a moving target. The models 3 months ago were much worse than they are today in a very like tangible way for the work that we're trying to do with them, and that will continue to change. What we're really trying to find as a sweet spot for our company, and I think where companies are going to have a lot of success, is finding a high leverage place where the models are not good at something today, where you can build a tool to make them much more capable in that area that unlocks some new area of capability generally for the models. So we see that, as what we're trying to do in sort of two directions as well. One is, well, we now have models that can design circuits, like fantastic, but we don't want to end up with the same problem we have over in the world of software, which is huge, like piles of code that no one knows what they do or how they work. So there's sort of two important focuses. One is making the models very capable, and then the other is inspectability, being able to understand what's being built here. Are we building the right thing? So, we're talking about requirements capture. Like, let's make sure we're on the same page. Here's what this device needs to do. And then how do we link that all the way through to some simulation testing to make sure we actually did achieve that, and to be able to thread through the whole design process there as well. So yeah, that's sort of the two lenses that we're looking at the problem through.
Now, there are a few ways to go about doing all of this, right? There's the purely graphical way, and we've talked to one company that's doing that. There's probably a mixed graphical and code method, and I think some listeners out there will know of a couple other companies that are doing that. And then there is, I guess, purely a code-based way to do this. And I think the graphical way kind of came first, at least from some of the early companies that were, getting into this area. And then now we're starting to see code-first kind of platforms, and that's really where you guys sit. So obviously, AI applied in software, it starts in code and ends in code because, those guys live in code. But at the end of the day, we live in, a CAD drawing, right? We have something graphical that represents the physical thing we're going to build. So I'm interested to hear from you guys. Why do you think a code-based or a code-first platform is really the best approach to developing PCBs with AI?
Yeah, so I mean, I'll add one thing to that. I think, just back to my sort of previous remark there, of we see two important things. One is we need a set of tooling, which is we see it as the language and then tooling around it that unlocks the model's capabilities. And any company in the space needs to figure out this. The second question is, how do you present that to the user in a way that allows them to build powerful things and understand them, as well as familiarity and being able to work within their existing designs with the team members that they have. So those are sort of the two competing like pools for us and any company in the space for sure. We really see it as, the first side is pretty obvious. We've got the code, we've spoken about that. The second side, we see two things. One is, everyone thinks schematics, like, makes sense. And yes, schematics make a lot of sense in some circumstances to represent your design. You're looking at some little analog circuit. It would be kind of annoying to read code to try to figure out what that does. A schematic is a much better representation. And so in our platform, we generate a schematic for you to view. We see it as an artifact to help you understand some section of the design. But you think maybe in like a primarily digital circuit, you're really looking at like a bus view, more of a block diagram, if you will, of your circuit. You want to see higher level, how do all these blocks connect together? Or perhaps from the perspective of a power tree or something like that. So we see there's really not just one way to represent this, and we take it quite seriously in that, we are visual creatures, and having a good visual way to communicate the design to a wide audience, both engineers, but firmware engineers as well, or other technical people, or even non-technical people working on the design. So yeah, that's kind of how we're thinking about the problem.
Yeah, almost like a multimodal approach where
Mhm.
you basically have one language that allows you to create all these different objects. I'm not an AI developer, right? You guys would know better than I do, but it sounds like you need to really develop an underlying translation between natural language or the code that we would use, which is kind of, I guess its own type of natural language, and then the file that you generate, which may or may not be human readable. I guess if it's an ASCII, it could be human readable.
Yeah, like I think a good way to think of this is like between deterministic layers and non-deterministic layers. Like the LLMs and AI in general bring us a whole set of non-deterministic tools that are great at solving problems that are just too complex of a search space to solve deterministically. But the problems that are easy to solve deterministically, the non-deterministic algorithms are really bad at, because they just take guesses, while in linear time or quadratic time, we could already solve them. And it is like one thing that I like to think of is humans are extremely intelligent compared to what else exists at the moment. But I'm still going to use a grocery list if I go shopping, even though I could remember all the items with enough thinking and with enough like bridges. I can do so, but it's going to take so much cognitive load compared to just a simple piece of paper that I just write on there. And this is kind of how we think of the split between deterministic and non-deterministic algorithms. Yes, with enough intelligence, you can do everything without an extra deterministic layer, but it's always going to induce extra cognitive load that will take away from the part that's actually hard to solve deterministically.
Okay. So you are trying to actually develop something that is repeatable when you talk about something that's, a deterministic algorithm,
Exactly.
right? If we could probably put in slightly different inputs in our requirements, right, depending on how it's phrased, but ultimately we get out, let's say an STM32 microcontroller schematic, right, with the same nets listed, same capacitors placed, things like that.
Yeah. So I mean, like our language looks, I don't know, probably a lot of people would be familiar with Python or something like that. It boils down to something that you would find somewhat familiar as a programmer. There's a language, you declare what exists in your design and how it's connected. It's not just a text document full of I need a microcontroller, etc. That's on the input side, as you would in a traditional design flow. You say, here are my high level requirements, here's roughly what the design looks like. But as that propagates through the design process, we end up with a deterministic design that every time you build it, you're going to get exactly the same thing.
So, given everything that you've been describing, one thing I'm very interested in, and I kind of had an epiphany about this recently, is what do you see as the designer's role, or how does the process change when you have these types of tools for creating schematics or even creating a PCB, maybe you're not creating all of the routing in the PCB, but maybe you're creating all the functional blocks, and you can start to kind of put them together and connect them how you want. What do you see as the process for this type of tool?
Yeah, we're thinking that there's like two roles in basically any application, like across all engineering industries. Is you have someone who needs to have a good system level overview, the system architect, and someone who has like niche knowledge for specialized, rare occurring challenges. So, in electrical engineering would be like your RF, black magic wizard would be like this very specific specialized niche where you probably don't want the AI to take over, do code or whatever. You really want to have full ownership over it. This is where you're innovating. This is what you want to own. And you can use the tools to help you. You can, for example, try to research together, try to capture the requirements. The code is still very useful for taking all this black magic knowledge of the wizard and putting it into a deterministic documented form for other people to interact with. But where we think it's going to grow more, like this is probably going to stay very similar. What's probably going to change the most, also what's happening in software, is that there's going to be less of those boilerplate engineers, people who draw symbols, people who build the same designs over and over again and the same routes. Like we really want to make what we think where it's going is that you become more of a system designer. We remove the cognitive load of the low-level boilerplate so you can focus on the holistic overview, and with this not only build faster but also build complex designs that were not possible before because they would have not fitted in your abstraction model. Like if we're thinking 5,000 component boards are pretty common today, but there's not a lot of 50,000 and 100,000 component boards because it just gets too much. Then you really want to split it out and think of the isolated units. But we think like the more we lift up people from not having to deal with the small details because you can trust the compiler and the deterministic layer and the models to do that right, the more you can focus on the top level overview and system architecture.
Yeah, I've talked about this kind of thing almost as I guess in two ways, right? There's the capability enhancer, and then there's the AI acting as like a junior engineer, because the task that you have just mentioned, I guess you could say eliminating the boilerplate tasks. I like that you use that term boilerplate because I hear the same term used in software to describe kind of the low level repetitive kind of copy and paste or mostly copy and paste code, but in the past someone still had to write it out. You still have that same thing in hardware where someone's making footprints, they're making symbols, they're entering all the manufacturer data, and they still have to do it all by hand. So I think that makes perfect sense, right? Your AI is basically like your junior level engineer, you're a librarian. And then you mentioned turning someone into a system level designer. I see that as the capability enhancement, where you can take somebody who has a reasonable level of experience, but now maybe they're able to work on something that they're not 100% familiar with, or they don't have, a huge amount of experience in, but they can at least like get in and get started on a new design by kind of taking this system level approach.
Yeah, for sure. I think you're really taking people from a junior or maybe senior level and elevating them to something that previously like a staff engineer would be working on from a capability standpoint.
And even more like you get people to a level that other people were already. But what's the exciting part is you get the best people and elevate them higher than was before possible. You get your best staff engineer that you already had, and he's getting even better. So that's where we see not only are we making people more efficient, more productive, that's a one axis, but also we are increasing the horizon of what's possible to be built in the first place.
So how do you see as the best way for designers to interact with this type of tool, right? Do they have to do it all through Visual Studio Code, let's say? Do you foresee integrations with, like Altium, let's say, where you access this through a panel? Currently, obviously, there is no atopile panel inside of Altium Designer, but would you like to see the atopile panel inside of Altium Designer?
Yeah,
is that kind of how you envision these things interacting?
I think useful to maybe take a small step back to answer this. So we really see where we can have the immediate highest impact is finding places where the tools are working well but are disconnected, and finding a way to pull them together with our language and our tool and our AI, etc. And so exactly, we use, for example, Altium, like the layout tools in that we use, so we connect with that, use them for layout. We don't have our own layout tool, that would be hard and annoying to build, and someone's already got one that works great. Same over maybe on requirements or simulation. We want to plug into those tools and be a layer initially that connects across all of those in a much more seamless way than is possible today.
Yeah, the same for auto routers. It's like currently one of the biggest problems of auto routers is that you have to redesign basically everything, because you already had to think about what components you choose, where they have to go in your schematic and your layout. But now to the auto router, I also have to communicate all those constraints again. If you capture them in our tool in the first place, you can use them both in your layout with ERCs and DRCs and so on, but also it automatically can flow into your auto layout tool and auto router, which not 100% there yet. They can't do huge designs, but in some places they can already be good. And if you have it already in there, you're ready for when the auto routers become good enough for big designs. So really think of us as a fabric connecting all those already great tools together and where their strengths are.
Sure, yeah, and as for those who have worked on complex projects, they're inherently multidisciplinary. So that kind of connecting thread, I think, is really important that you just brought up. But one interesting question that I have that just hit me, and I talked about this with some other folks, and this kind of comes up in the context of AI destroying all the jobs, is let's suppose you're successful, right?
Yeah.
And you are able to, let's say, save PCB design teams. I'll just throw out a number here, right? Let's say you're able to save them 30% of their workload, right? They've got 30% of their time back. What do they want to do with that time? Or what do you see that they can do with that time? And maybe here's a better question. Have you talked to potential customers or users? What have they told you that they would do with that time?
Yeah, I think, to me as a previous designer, it's super obvious. When I was designing boards, there was never enough time to explore all of the things that I wanted to try. There was always the timeline. We had to get the product shipped, and that meant we had to cut down, choose what things we would explore. Even if there was a lot of money on the table or something really interesting to build, just limited by how much time, how much resource there was available. So what I think is going to happen is companies are going to leverage that power for massive cost downs is a very obvious one. When we would just have like a sheet of a bunch of different things that here's a project, we can go research this, swap out this component, validate this, whatever it might be, save some millions of dollars. Things that have obvious return, but just there isn't the resources to do today. I don't think we have a surplus of engineers in hardware in particular. And I think it's actually trending the opposite direction. So I think there can be much more hardware built than there is today. We can try a lot more things than we try today. And I think there's a lot of exciting things to build for sure.
A lot of, especially in the periphery, like currently spinning up a test board for your application board is very expensive because you also need to lay out that whole thing. Well, if layout was cheaper and easier to do, now the whole barrier to build proper testers for your boards becomes way cheaper. This is I think where it's going. Like there's like a law for it, right? Is it like, I forgot the name of it, but basically the more resources you get, you're also going to use more of them. That's basically what we see.
Jevons paradox.
Jevons paradox.
Yeah,
that one. So that's kind of where we think it's going to go to. When you free up resources, that's going to be just used for something more valuable.
Yeah, I tend to agree, and I tend to kind of, I don't want to say mock, but laugh at a little bit the doomsday tech bros who think that these tools are going to cause everyone to lose all their jobs and we're all going to have to barely get by on UBI. I think if you just look back at the history of technology, especially like at the turn of the 1900s, when industrialized farming was really starting to grow, most people were farmers, and if you would have said, well, 1% of the population in the future will be farming, they would have said, well, what's everybody else going to do for work? And clearly we all survived and thrived just fine. So I think we'll probably see the same thing with PCB design. One thing that's also interesting about this is you mentioned the test board. aspect. And I 100% agree that the test boards often get skipped because of the schedule pressure, the cost. It's another thing we have to spin up. How do you see test board generation happening? Would you like, for example, if you could do it using this tool, would you spin up like variants and maybe produce like 4 or 5 variants, and kind of that gives you some, space that you can test within to really figure out if any of your high risk circuitry isn't going to work out?
Definitely. I see that in sort of the explore direction I was talking about earlier is, maybe early in your project, you're trying to figure out, which ICs do I want to use? What topology do I want for my power? Whatever else. And you might just, based on the schedule, need to make an educated guess, commit based on maybe not a lot of data that you have available to you. Whereas instead, if it was very quick, maybe a week, you can spin out 5 different ways to do something, make a little board that maybe even includes nice surrounding circuitry where you can just easily plug it in to all your test equipment, get useful data out where you can make much higher quality decisions based on that. I think we're going to get designs right the first time when we have an integrated board, because each little subsystem has been validated. We've made a good choice for it. We're very confident that it will work. And now we're just at this integration phase. What I think is really interesting as well is if you can do that well, where you capture, some data about this little circuit, now next time you want to use that in some other project, you understand its envelope. You understand, if I want to use this under some different circumstances, maybe I still have it sitting around, or maybe you just profiled it really well, where all that data can be fed back into the design process. And first time, without doing this research phase, because you've already researched that area previously, you can just apply that same knowledge to your next project as well.
Yeah, the risk reduction is something that I think most people don't really account for until the risk turns on them. And, they have to start throwing away boards. So you guys actually put together a short demo. And what we're going to do is go ahead and ask everyone that's listening on audio to head over to the Altium Academy YouTube channel and check out the video, and then you can see this short demo. So before we show the demo, if you could just describe to us what we're going to see in this demo.
Yeah, so it's like a little two-parter. The first is really what we were mentioning. We are looking here at an ecosystem. So the first demo is showing how we integrate with Altium, that you can just continue your layout design in Altium or import existing designs, like it's just a native plugin into your existing toolchain. And the second one is demoing. Of course, we've talked a lot about it, our agent, how it interacts with your design. We built a little flight controller for a drone in a little session.
Okay, let's go ahead and take a look. So this is really cool. I'm sure some folks in the audience are going to be really excited to see this kind of thing. And I'm hoping that they'll get in touch with you guys so that they can learn more. We're getting up here on time, but before we end the session, I want to ask you guys, what is on the roadmap for atopile in the future?
Yeah, for sure. So, I mean, we see a few things. I think looking a little further into the future, we really want hardware to be much more connected in the way that we build things. And so, we've spoken a lot about the horizontal, but also in the vertical axis. So this is across teams. How are we working with our firmware team, our manufacturing team, our testing team, supply chain, sort of everyone in a company. It's very easy to think about a product as something that a design team makes. But very soon you'll find, once you self-design, there are many other bottlenecks around the design process to make things happen quickly. And so we see, very soon we want to start supporting those periphery teams with the same quality of tools to make this whole process much more integrated end to end, not just this thin slice of the engineering org.
Yeah, and that doesn't go only along the horizontal. We don't only see the electrical engineering process as being disconnected, but also integration with every other team. Like in software, when we have APIs between backend and frontend, there's protobuf and there's only one definition layer. And currently in firmware, it's so weird. You have to read the schematic to build back the device tree, but you already had all this information, all the pin marks that you decided on is already there. Why do I have to retype it again in a different tool? So we really want to both horizontally and vertically integrate the engineering stack a bit more together to get the hardware people back together with the rest of the engineering team.
Yeah, I still continue to be a bit shocked at some companies that I talk to and that I work with. They still do over the wall engineering. They as much as folks here at Altium and in the industry more broadly have talked about collaboration and disciplines coming together to try and work on things more efficiently. It just still doesn't seem to happen, and I think the disconnected tools part of it is a big issue, right? I mean, Altium 365 has tried to do a good job of linking mechanical and electrical together, which is really important, using the MCAD co-designer tool. But now you're talking about not just mechanical and electrical but firmware, and this is something else I've talked about quite a bit. So I'm interested to see what your thoughts are on that, where it goes.
Yeah, so I think one of the most obvious ones is like device trees and pin muxes already.
Yeah.
Like it's a no-brainer. If I have my schematic capture in whatever form, like I already know what is connected to my microcontroller. Like we already support that you can just export the device tree out of our tool if you design it with us, because one of the things that the code helps you, we haven't really touched upon a lot of what the code really helps with if you go low level, but we have high level definitions of the buses. You're not talking about some electrical lines. We're talking about I2C, SPI, PCI Express. It is to the compiler, to the tool, it's known what you're connecting, which if you connect the IMU to your microcontroller on this I2C line, it's already well known, and we can have all the information to just spit out the device tree. You load it into your embedded Linux or into your Zephyr, RTOS, or whatever, and you're done. Firmware doesn't have to take into account anymore any pin muxing, or is this pin 19 GPIO B or whatever. And
yeah, that's definitely a one spot where you can get into a lot of errors, I'm sure.
Yeah, like this is one of those things where we were talking about earlier, about like translation and having an engineer in between. That the firmware guy has to ask a hardware guy about what were you thinking in terms of pin muxing here, and then hardware is pin muxing.
Yeah,
I was just making the layout easy by just connecting it next to each other. So that's like one of the obvious ones, but there's like a lot of non-obvious things too. Like if you already extracted a lot of information out of the data sheets for doing your electrical design, you also have the information for the firmware team of like, I need here some boot switches, or I need to get into those different configurations. Those are my data rates for my I2C. So much that you can extract out of there. Also, the system architecture design, hardware and firmware are so close in how we think of abstraction blocks, because everything is kind of like a tree, right? Like if you look at hierarchical schematics, basically it's just a tree. And the same as with code. code is also just a tree. You can't like call in circles. You really got to have like some form of at least under cyclic free graph. And if we take this file tree of hardware and just get it over into software, have already like a little bit of a structure, and you just have to fill in the little drivers and whatever, that's also such a huge boost. And from then on, just like you can reuse the hardware modules, we can package the software too. Like imagine a little AD 1938 ADC or whatever. We ship already the little .atto file which describes the design, the layout, the driver circuit, but also the little driver.c that you can now just link into your project. Like, why rewrite that thing? Just have it all packaged as one atomic thing that is well tested. It has an automatic testing module that was generated for it. You run the driver in a in your test module that you printed out, and then this is a verified part for the librarian. And from there you go to the mechanical stuff on top of it. This is kind of once you start with those things and try to package them together, you see how intertwined actually everything is for how much we're trying, as you said, to over the wall.
Yeah, I think one for me, thinking about it, is definitely over in supply chain. Like when you're picking parts, and there's this really painful back and forth of, I specified some 10K resistor, 042, whatever, and now it's out of stock. Like, why does that need to trickle all the way back up to me as the design engineer? Why are these other teams not empowered with an understanding of the requirements? Like, what was I looking for when I picked that part, in a way where they don't have to come back to me not knowing anything about the problem? They can come back to me and say, like, here's some good candidates. These should work. What do you think? As opposed to, what is this part? I have no idea what's going on here. So I think, really a lot of those periphery teams that maybe don't get as much love as they deserve in making the designs ship out. I think there's a lot that we can do there that's going to be quite empowering and really make the whole process a lot smoother than it is today. I think maybe part of that for me is living through the sort of supply chain crisis as an engineer. I spent a very long time doing exactly that. And I just couldn't understand, because I would have to go back, look at some design that some engineer 5 years ago had made, and try to make sense of it. I don't know what they did. They maybe, if I was lucky, had some notes scribbled around, but definitely not enough to come to a good conclusion as to, will this part work or not, unless I just spec for spec match everything in the datasheet for it, which isn't necessarily correct. They might have just not cared and just picked the first part that they saw. So I think capturing things in a way where later the intent is understood is going to be huge for those sort of periphery orgs as well.
Well, listen, guys, as all of this rolls out and you start taking your product to market, I'd love to have you come back on and talk to us some more. It's a really interesting time in hardware design. I feel like we've turned a corner and there's just a ton of innovation all of a sudden, and you guys are in the trenches working on it. So I want to thank you both for being here today.
Yeah, it was super fun. Thank you so much.
Thanks so much for asking us out. It was really fun.
To everyone that's out there listening, we've been talking with Yanni Papamanoglou and Narayan Powderly, co-founders of Atopile. If you've been watching on YouTube, make sure to hit the like button, hit the subscribe button. You'll be able to keep up with all of our podcast episodes and tutorials as they come out. And last but not least, don't stop learning, stay on track, and we'll see you next time. Thanks, everybody.